All right, welcome back, Algebra 2. So the next thing we want to try our hand at is simplifying some nth roots, okay? So just to kind of warm it up a little bit, just to kind of remind you of what we're doing here. So let's say that I gave you the square root of 20 and I asked you to simplify that, right? You'd pretty much, there's a lot of different ways to do it, but one way is to kind of factor this down as much as we can. So we can think of 20, 20 factors down to one of the ways is 4 times 5. And then 4 is 2 times 2. So then the prime factorization of 20 is 2 times 2 times 5. So this is equal to 2 times 2 times 5. And what I want to do is factor these out as pairs, right? So 2 times 2, that's 4. And why did I kind of go backwards a little bit? Well, because now I know that 4 is a perfect square. So I get square root of 4 times square root of 5 using my properties of square roots. 4 square rooted is 2, square root 5. Okay, so we're pretty much going to be doing the same idea, same thing, but now with higher degree nth roots. Okay, so now we're going to be using cube roots, fourth roots, and fifth roots. Okay, so let's try it with this first one, the cube root of 40. Okay, so let's think of what 40 factors down to. Let's do the prime factorization. Some factors that we might see already are 4 and 10. Both of these can still be factored. 4 is 2 times 2. And then 10 is 2 times 5. So this is our prime factorization right here. 2 times 2 times 2 times 5. Okay, so I can rewrite the cube root as the cube root of 2 times 2 times 2 times 5. Okay, now I can think, if I think about the square root of 20 example, that was going to be 2 times 2 times 5, right? We rewrote the 2 times 2 as 4, but really what we could do is, since it's a square root, what we're doing is we're factoring out in pairs. If I have a pair of 2's, then that comes out as a 2, right? That's kind of what we ended up with when we did this piece. Now with the cube root, don't forget the index here, right? With the cube root, that tells you the groups that you have to factor out in, right? So with the cube root, I need to factor out in groups of 3. So if I have a group of 3 2's, then that can come out as a 2, right? So that's going to be 2 cube root of 5. Okay, and why is that true? Well, what is 2 times 2 times 2? That is equal to 8, right? Times 5. So cube root of all this right here. And we can do the same thing. We can split cube roots up across multiplication. So we get the cube root of 8 times the cube root of 5. And we know the cube root of 8, it's 2. Because what number do you multiply by itself 3 times to get 8? 2, right? So that's kind of another little trick we can use for simplifying radicals, in this case, nth roots. We go ahead and whatever number is here, the index, that tells us the size of the groups you're looking for, right? So if I want to factor something out, then it has to come in groups of 3. So triplets kind of, right? I need to find a triplet of 2's if I want to be able to factor out anything, right? Okay, so now let's go ahead and try another example. Let's try it with the fourth root here in part B. Okay, so that 4 is telling me that I want to find quadruplets, right? So quadruplet factors. I want to be able to find groups of 4 factors. So the first thing we want to do is go ahead and factor it down. So let's talk about 243. It's kind of a big number, but when in doubt, just kind of divide some numbers into it, right? We know 2 can't go into 243 because it's not even. So let's try 3. 243 divided by 3. That's 81, right? So we know this is 3 and 81. Oh, and then 81, we know that's 9 times 9. And we know 9 is 3 times 3. So this is our prime factorization. How many 3's do we have? We have 5. So this is equal to the fourth root of 3 times 3 times 3 times 3 times 3. Okay, so we're looking for quadruplets. We want a group of size 4 to factor out, okay? So how many groups of 4 do we see? We only have one group of 4 right here. we have 4 3s. And so that is what we're going to be able to factor out. And it comes out, even though there's 4 of them, it only comes out as 1 3. Why? Let's talk about it again, right? What's 3 times 3 times 3 times 3? Well, we kind of know that, right? These 3's came together to give us 81. So that is going to be 81 times 3 under the 4th root. And then again, we can separate across multiplication. This is the 4th root of 81 times the 4th root of 3. And the 4th root of 81, what times itself 4 times gives us the 81? Well, that's 3, right? So we have 3, 4th root of what's left? 3. Let me write that a little bit nicer. 3, 4th root of 3. Okay, be careful that you kind of separate the 3 away from that 4 because you don't want to confuse yourself and think that it's 3 to the 4th power. This is 3 times the 4th root of 3. Awesome. Let's do one more. Okay, the 5th root of 96. Okay, so now it's groups of 5. We want, is there a word for it? Quintuplets, right? Instead of just triplets or quadruplets, we want quintuplets, right? Groups of 5. Groups that have 5 of the same thing in there. Okay, so first thing we should do is factor down that 96. Okay, so 96, if we don't know what goes into it, let's just start small. We don't really care about 1 because 1 goes into everything. Let's start with 2. This is even, so 2 will definitely go into it. 96 divided by 2 is 48. So 2 and 48. Oh, and then 48, we know that's 4 times 12. 4 is 2 and 2. And then 12 is 6 and 2. So let's just put the 2 here and then 6. And then we know 6 is 2 and 3. So here's our prime factorization. 2, 2, 2, 2, 2, 3. So the 5th root of 96 is the same as the 5th root, a long 5th root of how many 2's do we see? 5. Oh, we kind of have our answer already. Times 3. Okay, so I have a group of 5 2's here. I have a quintuplet of 2's. So that can come out as just 1 2 again, right? If you take out a group of something, it's only going to come out as that one number, right? So if I take out a group of 5 16's, it's only going to come out as a single 16. Okay, so 2, 5th root of what's left? 3. So then there's our answer. Okay, these are all our answers. Okay, notice that each of these examples started off as nth root notation, the radical notation. So I want to give an answer in radical notation. Okay, but all of these I could have went back and expressed in exponential, for example, with this last one. The 2 is alone, so I'm just going to leave the 2 there, but then it's going to be 3 to the 1/5 power. This one right here, it's 2 times 5 to the 1/3 power, and this one is 3 times 3 to the 1/4 power. Okay, cool. So we kind of cheated a little bit. We used some properties that, kind of made sense to us. If we can do it with square roots, we can do it with nth roots. That kind of is uh, not a good, not always true, but in this case, it worked for us. And that's why I kind of said we cheated a little bit. But let's go ahead and make it right and write down the actual properties, right? So with square roots, if you remember, I was allowed to say if I had the square root of a times b, then that's equal to the square root of a times the square root of b, right? Which is why we're allowed to separate the root across multiplication and division, right? If I have the square root of ab, that's equal to the square root of a over the square root of b. Okay, and then both of these work backwards, right? If I start off with a product, I can go backwards and write it as one radical. Same with the division. If I have the square root of a over square root of b, I can go backwards and write it as the square root of just the fraction, okay? So we cheated a little bit, but it is true. This works for nth roots in general, right? So we can put an n for all of these radicals, okay? So again, kind of something that we already learned. Now we can apply it to what we're learning right now. Okay. So let's go ahead and finish off section 6.2a with two more examples, two more pieces. One more example, example 3, but has two pieces. We're going to multiply and divide the following nth roots, and then we're going to try to simplify if we can. Okay, so we're kind of applying what we just learned in example 2, and then taking it an extra step, okay? So let's start with A, the cube root of 108 times the cube root of 4. Now, eventually it's going to want us to simplify. So why don't we kind of just do that now? Because if we have everything simplified immediately, at the end when we get our answer, since everything was simplified, it's going to most likely already be in simplified form. Okay, so let's try simplifying now. So let's think about the cube root of 108. Okay, let's think about the number 108. What can I break it down to? We probably don't really know off the top of our heads, but again, let's try dividing some numbers into it. So does 2 go into it? 108 divided by 2. Yes, 2 times 54. Okay, and then what about 54? We know 9 and 6 is 54, correct? Yes. Okay, so we can separate that into 6 and 9, and then 6 is 2 and 3, and then 9 is 3 and 3. So there's our prime factorization, 2, 2, 3, 3, 3. So cube root of 2, 2, 3, 3, 3. This is all for the cube root of 108. And I have, my 2 is in a pair, so I can't take that out. But I do have a triplet of 3's, so I can take that out as a 1, 3. So 3 cube root of 2 times 2 is what I have right now. Now I could multiply those 2's back together, but probably with our final answer, we're going to try to keep simplifying as much as we can. Let's probably leave it like that in case we can take out a triplet of 2's eventually. Okay, so with this cube root of 4, if I didn't know any better, I could have tried to simplify that, right? Because the 4 is 2 times 2. So that's the cube root of 2 times 2. But I can't take anything out of there, so it has to stay like that. Okay, so now I have 3 cube root of 2 times 2 times cube root of what was originally 4 is now cube root of 2 times 2. So now I have 2 cube roots. They're the same index. Because they're the same index, I kind of forgot to mention it. You can only write them under the same radical if they have the same index, right? If this was a cube root and this was a fourth root, we couldn't do it, all right? So it's cube root of 2 times 2 times 2 times 2. Oh, look, we have a triplet right here, a triplet of 2's. So that's going to come out as a 2. So I get 2 times 3 cube root of 2. 2 times 3 is 6. So 6 cube root of 2. Okay. What we could have done is we could have also just multiplied 108 by 4 and then went from there and broke it down and saw that we could have done that as well. Okay. It doesn't matter how you do it, right? As long as you do it. Let's try the last one. Okay, division. We can go ahead and divide them on the inside. Now, division is a little different. When I divide something, it gives me something smaller, and we like working with smaller numbers. So with this one, let's go ahead and immediately just divide. So I can write this as the fourth root of 160 over 5. And what is 160 divided by 5? That's 32. So I'm asking for the fourth root of 32. What's 32 factored down to? Well, that we know is 8 times 4. And we know 8 is actually 3 2's, right? And 4 is 2 2's. So I have the fourth root of 2 times 2 times 2 times 2 times 2. Okay, how many quadruplets do I have? I have one quadruplet of 2's. So that comes out as a 2, and I have left the fourth root of this singular 2. So that's my answer. Okay, hopefully it's okay. Hopefully you're kind of agreeing with, yeah, this is kind of stuff we've already seen before, but now I'm applying it to higher indices, higher nth roots. Okay, the procedure is kind of the same, but now we just got to take care of a few more details, a few more things to look out for. All right, I'll see you in class so that we can practice this stuff together. Okay, have a good rest of your night, your day, whatever time you're watching this, and I'll see you next time.